What if the universe we thought we understood was about to crack? For years, something subtle but deeply unsettling has been simmering in cosmology. The universe looked too smooth. Not enough clumps. Not enough gravity pulling matter into the tangled cosmic web we expected. And that may sound minor, but if true, it meant one of three things. Einstein was wrong. Dark matter behaves differently than we think. Or the entire cosmic timeline, from the Big Bang to today, was miscalculated. Two measurements of the same universe were disagreeing. Two clocks ticking out of sync. But now, a new dark matter map just dropped. Sharper, cleaner, independent of the previous weak points. And it may have just settled the fight. You've seen the headlines. Is the universe too smooth? Here's the twist. Our new dark matter map says no. Using ancient light from the cosmic microwave background as a backlight, scientists traced the invisible scaffolding of the cosmos and found it lines up with Einstein's predictions. Stay with me to see how gravitational lensing lets us see the unseen, why earlier maps looked fuzzier, and how this high-resolution view bridges the baby universe to the web of galaxies we see today. If you've been confused by conflicting reports, this is the map that makes sense of it. If gravity has had 13.8 billion years to pull matter together, why did some recent surveys say the universe looks too smooth? Astronomers call this the clumpiness problem. Under the standard model of cosmology, ΛCDM, guided by General Relativity, tiny ripples in the early universe should grow into a cosmic web with a specific level of lumpiness. We quantify that growth using parameters like sigma₈. Think of sigma₈ as a measure of how strongly matter clusters on scales of about 8 megaparsecs, roughly 26 million light-years. It tells us how bumpy the universe is at those scales. Then there's S₈, a related parameter that folds sigma₈ together with the overall matter density of the universe. S₈ is often what lensing surveys report. And here's where things got interesting. Several weak lensing surveys, projects that infer mass by measuring how galaxies subtly stretch and distort background galaxies, reported S₈ values suggesting less clustering than expected. Not wildly off, but consistently low. Enough to raise eyebrows. Enough to whisper, is something off? When teams like KIDS and DES measured galaxy-weak lensing, their preferred S₈ sketched a smoother universe than the early universe blueprint implied by the cosmic microwave background. Meanwhile, the Planck satellite had mapped the CMB with exquisite precision. Its temperature and polarization patterns pinned down cosmological parameters with tight uncertainties. Project those early universe conditions forward in time under ΛCDM, and you get a specific prediction for how clumpy the universe should look today. But the galaxy surveys were dipping below that prediction. A mild tension, not catastrophic, but persistent. And in cosmology, persistent tension is where revolutions begin. If the universe truly grew less lumpy than predicted, something fundamental would have to change. Maybe dark matter isn't perfectly cold and collisionless. Maybe it interacts slightly. Maybe gravity weakens on ultra-large scales. Maybe dark energy influences growth differently than we assumed. Or maybe neutrinos, those nearly massless particles streaming through everything, damp structure formation more than expected. Each possibility rewrites part of modern physics. Think of it like this. Imagine two clocks set at the Big Bang. One clock is the CMB. It records the early conditions with incredible precision. The other clock is late time structure, galaxies, clusters, the cosmic web we see today. If the model is correct, both clocks tick in harmony. But if one runs slightly slow, either we misread one of them, or something has been tugging on the gears of the universe for billions of years. Planck gave us an extraordinary readout of that first clock. But its CMB lensing map, The map that traces how matter bends the CMB was relatively coarse. It read the letters of the cosmic story with a thick marker. That left space for debate. Because galaxy lensing, the other method, comes with baggage. Galaxy lensing requires precise measurements of galaxy shapes. Tiny biases in shape estimation can create artificial shear signals. Galaxies also physically align with local tidal fields, mimicking lensing distortions. Photometric redshifts, distances estimated from galaxy colors, introduce calibration uncertainties. Atmospheric distortion and detector noise can leak into measurements. Teams carefully model these systematics. They simulate them, cross-check them, calibrate against them. But when differences are subtle, even tiny residual biases can shift results. So what if we removed galaxy shapes from the equation entirely? What if we weighed the universe without using galaxies as our rulers? Instead of measuring how galaxies distort, use the oldest light in existence, the cosmic microwave background, a 13.8 billion-year-old glow, a perfect backlight behind everything. Reframed like this, the question becomes clean. Lens the oldest light. Measure how strongly it's deflected. Infer how clumpy the cosmic web really is. No galaxy shape biases, no alignment effects, just gravity-bending ancient photons. This is where the Atacama Cosmology Telescope comes in. High in the Atacama Desert, about 5,200 meters above sea level, ACT observes under some of the driest, clearest skies on Earth. Its detectors measure minute temperature fluctuations in the CMB, variations just tens of microkelvin. But more importantly, it measures polarization patterns. Because gravitational lensing doesn't just shift hot and cold spots, it subtly twists polarization. Here's the key idea. Massive structures between us and the CMB bend its path. Every galaxy cluster, every dark matter filament, every overdensity along billions of light years. Each one deflects the ancient light slightly. Individually, the effect is tiny, but across millions of pixels, it forms a coherent pattern. Like looking through frosted glass, you can't see the glass directly, but you can infer its texture from how it smears the background. In this case, the glass is the entire cosmic web. Planck mapped this effect across the whole sky. But ACT sacrifices all sky coverage for sharpness, arc-minute scale resolution, cleaner reconstruction, sharper recovery of small-scale structure. That extra resolution tightens the measurement of the lensing amplitude. To extract the signal, scientists use statistical tools called quadratic estimators. They look for specific correlations lensing introduces between modes in the CMB map. Temperature data provides strong signal. But polarization, especially how lensing converts E modes into B modes, adds a powerful independent check. Foreground emissions, like galactic dust and hot cluster gas, have different frequency signatures. ACT observes in multiple frequency bands. That allows researchers to separate cosmic signal from foreground noise. Bright clusters are masked. Null tests scramble data to ensure no artificial signal remains. Simulations inject fake universes into real noise to confirm the pipeline recovers the correct answer. This isn't casual astronomy. It's precision cosmology. So here's the moment of truth. With this sharper, cleaner CMB lensing map, does the universe show the level of lumpiness predicted by ΛCDM and General Relativity? Yes. Within statistical uncertainties, it aligns. The lensing amplitude matches early universe predictions. The scale dependence fits. The two clocks agree. And that matters. Because if the result had gone the other way, if the universe truly were smoother, we'd be staring at new physics, modified gravity, exotic dark matter interactions, unexpected neutrino mass effects. But instead, Einstein survives again. ΛCDM holds. The baby universe and the mid-aged universe tell the same story. But this isn't the end. Sharper polarization data is coming. CMB-S4, the Simons Observatory. These next-generation experiments will push lensing reconstructions even further. They'll test gravity more precisely, weigh neutrino masses through their subtle suppression of structure growth, map how dark energy influences cosmic expansion and clustering over time. The scaffolding of the cosmos will come into even sharper focus. So the universe isn't too smooth. It's exactly as structured as it should be. For now. And that's almost more fascinating. Because the mystery didn't vanish. It evolved. Do you want a deeper dive into how CMB polarization sharpens lensing maps? Or how neutrinos leave fingerprints in structure growth? Because the next generation of dark matter maps may not just confirm gravity. They may test it at a level we've never attempted before.
Thanks for watching. If you enjoyed this journey through the cosmos, hit like, subscribe, and tap the bell. And when you're ready for your next space mystery, click the video right here.